First law of thermodynamics. First law of thermodynamics states that the amount of heat supplied to a system is equal to the sum of increase in its internal energy and the work done by the system against its surroundings. So if Q is taken as the heat, U is taken as the internal energy, W is taken as the work done. Q can be written as U1 minus U2, where U1 minus U2 is the change in internal energy, W is going to be the work done. So I can write Q is going to be the heat, U is the internal energy, or rather if I write delta U, it is going to be change in internal energy, which is going to be U1 minus U2. W is going to be the work. For small energy transfer between system and its surroundings, mathematical form for the first law of thermodynamics can be written as dW or dQ is going to be equal to dW plus du plus dW. This is going to be the mathematical form of first law of thermodynamics. We'll take up a numerical based on the same. A sample of ideal gas gamma is equal to 1.4 is heated at constant pressure. If an amount of heat 140 joule is supplied to the gas, find the work done by the gas. Right? Now, let me tell you what is gamma. Gamma is the ratio of Cp over Cv. Specific heat at constant pressure divided by specific heat at constant volume. That value is gamma and that is given over here as 1.4. So let me write this is equal to 1.4. All right. Now let me come back over here. At constant pressure, first they have given a sample of ideal gas is heated at constant pressure. If let me consider, let the state of the gas, let the state of the of gas change from, pressure is constant so only volume and temperature is going to change. V1 T1 is going to be the initial volume, final volume is going to be V2 T. The heat which it has to be is going to be dq, or I can write q is going to be equal to ncp delta t. N is going to be the number of moles, nothing is mentioned, so you can take n is equal to 1, where n is going to be the number of moles. You can take this to be 1 as of now. So I will be getting Q. They have already given to me, it is going to be 140 joules. So let me write down the same. Q is already given as 140 joules. So I can write NCP delta T. Delta T is T1 minus T2. So that is going to be equal to 140 joules. NCP delta T is going to be 140. I will be taking this as equation number 1. Now, I need to find out the change in internal energy first. So I will be writing change in internal energy. Change in internal energy is given by delta U is going to be NCV delta T. NCV delta T. Now, I can multiply and divide. Multiply and divide by C. When I multiply and divide by Cp, will I be getting delta U is equal to N CV divided by delta Cp multiplied by Cp and delta T. I have just divided and multiplied Cp on the RHS. All right. Now, I already know the value of NCP delta T. So I will be taking NCP delta T. The value of NCP delta T is 140. So I can write delta U. The change in internal energy is going to be 140, right? Multiplied by CV and CP. So what is CV and CP? CV divided by CP. Do I know what is CV divided by CP? I know what is CP divided by CV. So what is going to be CV divided by CP? Can I write this as 1 divided by 1.4? It is just going to be the reciprocal. I will be multiplying with 1 divided by 1.4. When I divide, I will be getting the value of delta U is going to be equal to, it is going to be 100 joules. 100 joules. This you can take as equation number 2. Now, what is asked? Work done by the gas is asked. You know from the first law of thermodynamics that Q is going to be equal to, or yes, you can write in any form. Q is equal to delta U plus W. Delta U plus W. This is your first law. In order to find out your work done, you can write W is equal to Q minus delta U. So work done is going to be Q which is 140 minus U delta U which is equal to 100. So the work done is going to be 40 joules. Is it clear? We'll be moving on to the applications of first law of thermodynamics. First, we have isothermal process. Isothermal process is a process in which temperature remains constant, right? When temperature remains constant, even the internal energy will remain constant. So I can write over here delta U, which is going to be the change in internal energy in case of isothermal process, that is going to be equal to 0. Now, substituting the same, n dq is equal to du plus dw. The first law of thermodynamics, I will be getting the value as, anyway, delta u is equal to 0. So I will be getting dq will be equal to dw. dq is equal to dw. So I can write heat supplied in the isothermal process is used to work against the surroundings. So here the heat supplied is going to be equal to the work done in case of isothermal process. In case of adiabatic process, a thermodynamic process in which there is no heat transfer, it is called adiabatic process. If there is no heat transfer, then can I tell dq is the heat, that is going to be equal to 0. In case of adiabatic process, substituting the same in dq is equal to du plus dw. I think somebody is in the class. Let me just check. Yeah. Substituting the same in the first law of thermodynamics, I will be getting du as 0. So 0 will be equal to du plus dw. Shifting any one to the other side, I will be getting the value as du will be equal to minus dw, or vice versa. So in the case of adiabatic process, the internal energy and the work done is going to be the same. The magnitude is going to be the same. However, the sign is going to be different. Isochoric process is a thermodynamic process in which volume remains constant. So I can write over here delta V is equal to 0. Can I do that? Yes. When delta V is equal to 0, right? That is what your isochoric process is. Now, work done is given as P delta V. P delta V. If V is equal to 0, even W will be equal to 0, because W is equal to P multiplied by delta V. Now, substituting the same in the formula, dQ will be equal to du plus dW. Substituting in the first law, I will be getting W is equal to 0. In this case, what will be equal? dQ will be equal to d, meaning that the heat supplied is going to be equal to the change in internal energy. Isobaric process is a thermodynamic process in which pressure remains constant. Again, if pressure remains constant, can I write P delta P is equal to 0? Yes. Yes, delta P is equal to 0. Now, I will be taking dq is equal to du plus dw. This is your first law. When I substitute delta P is equal to 0, I don't see any delta P. So what is going to happen? The first law will remain unchanged in isobaric process. So heating of any liquid at atmospheric pressure or heating of any gas at constant pressure, you can consider this. Okay. In this case, du and dw both are not 0. Next, we have a few limitations of first law. First law fails to explain the following points. Why a heat flows from hot body to cold body. We know that it flows from hot body to cold body, but however, there is no proper explanation as to why it is that way. Another uh, limitation is that it doesn't explain the condition under which the heat can be converted to work. Right. So these are the two limitations of first law of thermodynamics. Next, we are going to consider heat engine. Heat engine is a device which converts heat into mechanical energy. A heat engine essentially consists of three parts: source, working substance, and a sink. Source, temperature of the source is going to be a constant and it can supply any amount of heat at this temperature. Working substance, it is an enclosed thermodynamic system which can do work. Sink, it can absorb any amount of heat while maintaining its temperature at constant level of the sink is less at constant temperature, and the temperature of the sink is always less than temperature of the source. So if you consider a heat engine over here, the sink is can be taken as T2. The temperature, if I take it as T2, the temperature of source, if I consider it as T1, always T1 is going to be larger than T2. The temperature of the source, it is going to be larger than the temperature of the sink. Work done is given by the difference in the heat Q1 minus Q2. That is how you are going to calculate your work done. Now, let me come to the principle of the heat engine. Principle of heat engine. The working substance, which I have discussed over here, absorbs the heat from the source and converts a part of it into work. So, your working substance, it is going to collect heat from the source. Then it is going to reject some of the heat, and little amount of heat is going to get converted into work. Right? Now, if I consider Q1 to be the heat which is supplied by the source, Q2 to be this heat which is supplied by the working substance to the sink, then the work done W will be given by Q1 minus Q2. So I can write over here the work done dW is going to be equal to Q1 minus Q2. This is going to be the work where Q1 is the amount of heat absorbed, W is the total work done, Q2 is the amount of heat rejected by the working substance. All right. Now, if I substitute the same, I will be how can I get this equation? It is very very simple. From the first law. So from the first law, I know that dq is going to be equal to du plus dw. Right? Now, net amount of heat absorbed. What it is going to be, as the working substance returns to its original state, the internal energy is going to remain constant. So I can write over here delta U will be equal to 0. Since delta U will be equal to 0, this can be taken as 0. dW will be equal to dQ. The same thing I have written over here. dq can be written as q1 minus q2. Next, we have efficiency. Efficiency. Efficiency of a heat engine is defined as the ratio of net work done per cycle by the engine to total amount of heat absorbed. So if I have to write it in form of a formula, let me write it in form of a formula. So it is represented by the letter or the symbol eta. Okay, this is spelled, or this is called as eta. So efficiency of the heat engine is defined as the ratio of work done. So I can write work done, which is going to be W, right, or dW, the change in work done, divided by ratio of the work done per cycle by the engine to total amount of heat absorbed. Total amount of heat absorbed, it is going to be Q1. Now, dW is Q1 minus Q2. So I can write eta as, eta can be written as, which is your efficiency, Q1 minus Q2 divided by Q1. This is going to be your efficiency. And of course, you have to multiply this with 100 in order to get your efficiency in percentage. So efficiency is always represented in percentage. It is given by dW divided by Q1, which can be written as Q1 minus Q2 divided by Q1. Let me write the definition as well. It is the ratio of net work done to the total amount of heat that is absorbed. Heat which is going to be absorbed. Is it clear? Now, we are we will be taking a problem based on the same temperature of source and sink. Source and sink are 300, 400 and 300 Kelvin. 400 and 300 Kelvin. Find out the efficiency. Find out the efficiency. Now, source temperature of source and sink is given. Or let me reconsider this problem as this way, because I can take the other way also, but let me take q2 q1 minus q2. So I will be writing over here the same problem. I will be writing heat absorbed by working substance is 400 joules. Heat rejected by working substance is 300 joules. You have to find out the efficiency. Find out the efficiency. Right. Now, let me make a note of what they have given to me. 400 joules and 300 joules has been given. Heat absorbed by the working substance is 400 joules. Heat rejected by the working substance is 300 joules. So let me go over here. Q1 is going to be the heat which is going to be absorbed by the working substance. Q2 is going to be the heat which is going to be rejected by the working substance. So Q1 is going to be equal to 400 joules. Q2 is going to be equal to 300 joules. What should I be finding out over here? I have to be finding out the efficiency. I know the formula for efficiency. Efficiency is given by dW divided by Q1. dW is nothing but Q1 minus Q2 divided by Q1. Right? What is your Q1? Q1 is going to be, of course, you have multiplied by 100 as well when you represent that in percentage form. 400 minus 300 divided by 400 multiplied by 100. So you will be getting eta as 100 divided by 400 multiplied by 100. Two zeros and two zeros can be cancelled. Now eta is going to be 5%. Eta is going to be 25%.